High-density aquaculture pushes biological limits. When you pack hundreds of kilograms of fish into a single cubic meter of water, survival relies entirely on the accuracy of the flow models predicting oxygen distribution. If the math fails, the stock suffocates. To evaluate these models, engineers look for what is known as the numerical killing zone. This is a two-axis diagnostic space where a computational grid fails simultaneously on two fronts: precision stress, where eigenvalue conditioning collapses, and observable disintegration, where the support structure falls apart. Previous testing on chaotic models demonstrated exactly how fatal this zone can be. When the complex twisted bird map geometry was run through the Ulam matrix framework, 9 out of 10 subdominant tiers fell directly into this joint failure state. The calculations became useless. Paper 61 proposes a structural fix. Instead of evaluating pathological shapes, the study audits a strictly depth-averaged 10 by 10 meters square tank Ulam operator. In computational fluid dynamics, geometry dictates stability. A flawed shape traps the matrix in the killing zone, guaranteeing a cascade of physical failures on the factory floor. The proposed grow-out model establishes a rigid baseline, a 10 by 10 meter square footprint with a 1 meter water depth. The model incorporates wall jets to simulate the return flow from the filtration system and specific drain patches to extract waste. This blueprint outlines the core geometry. Blue flow lines map the bulk mixing core, tested across 5 drain placements, center and the 4 corners. To ensure these findings held up at scale, the execution locked in grid dimensions at n equals 64, 128, and 256. The finite-grid verdict is clear. Across all 5 drain setups and all 3 executed grid sizes, exactly 0 tiers entered the joint precision and observability killing zone. The square tank completely avoided numerical collapse. This stability reveals itself in the geometric mixing penalty, or DGM. Earlier cylindrical models produced measurable support ratio stress, yielding penalties around 1.22. The square tank, however, achieves a numerically flat support ratio, locking in a perfect DGM of exactly 1.0. The square footprint acts as an analytically safe computational domain. When applied to rigid, untwisted geometries, the Ulam transfer method holds its structure without failure. While the static tank holds the stock, the water quality is governed by the mechanical lungs of the farm, a continuous filtration loop. This diagram illustrates the cascading architecture of the life support system. It plots a sequential journey of water through an 8-node processing loop. The flow drains into the drum filter for mechanical extraction, cascades through a sand filter, skimmer, and UV unit before hitting the biological stages: biofilter, oxygen cone, trickling filter, and the submersible bed. Modeling this flow introduces a computational trap. If you attempt to couple all 8 nodes into a single massive 8n by 8n matrix operator, the intersecting variables compound any systemic errors, making the model incredibly fragile. In engineering diagnostics, forcing unnecessary mathematical complexity obscures the actual mechanical threats. The math becomes the point of failure instead of the hardware. To prevent this compounding error, the analysis dismantles the loop into a block operator. Each of the 8 nodes is mathematically decoupled and evaluated as an independent stirred tank environment. Rather than wrestling with an unwieldy coupled system, the framework isolates the components into smaller identical matrices, evaluated entirely on their own. Tested individually at n equals 32, the results mirror the square tank. Every single stirred tank node remains safely outside the killing zone. The sequential architecture introduces 0 new mathematical pathologies. Regarding grid failure, the loop is completely benign. This schematic of the loop shows us where the actual operational constraint lies. It is dictated by the chronological flow, a fixed loop residence time of 20.3 minutes to process toxins and return the water. Decoupling the matrices acts as a diagnostic firewall. It ensures that complex equations don't interfere with establishing rigorous baseline capacities for the hardware. Once the math is stable, it must be applied to the physical realities of a pump failure in a maximum capacity holding tank. A halted pump triggers 2 distinct chemical threats. Without the return jet, ammonia slowly accumulates in the water column, while dissolved oxygen drops rapidly. At 300 kilograms per cubic meter, oxygen hits lethal limits in exactly 6 minutes. 6 minutes is far too fast for manual water sampling or human intervention. Surviving this window requires an uncompromising mathematical rule for deploying automated biosensors. It must dictate a rigid operational schedule on the factory floor. To prevent a catastrophic drop, operators use the two-channel revisit inequality formula. This formula calculates maximum safe time away from a tank, critical failure window divided by twice the geometric penalty. In the revisit bound summary, a 6-minute critical window divided by 2 forces a maximum revisit time of 3 minutes for dissolved oxygen. The ammonia channel is tied to the loop's residence time. With a 20.3-minute window, the sensor patrol gets a slightly more forgiving maximum revisit time of 10.15 minutes. A 3-minute oxygen patrol across thousands of tanks is physically impossible for mobile robotic sensors. That strict mathematical bound means static oxygen probes are completely non-negotiable for every single tank. The revisit inequality directly ties grid mathematics to robotic logistics. It replaces informal guesswork with hard numbers, mandating exactly what hardware is required to keep the stock alive. It is critical to state the limits of this audit. These conclusions are strictly finite-grid diagnostics, calculated on resolutions up to n equals 256. They make no claims about continuous fluid dynamics or behavior at infinite asymptotic limits. This limitation perfectly mirrors real-world deployment. Robotic sensors do not read data in a continuous spectrum. They process their environment in distinct, finite numerical blocks. Evaluating deeper, finer grids might reveal new non-normal flow effects, but those discoveries would still require rigorous proof within this exact same diagnostic framework. Engineering safety relies on defining absolute operational boundaries, not on achieving infinite mathematical precision. In earlier analyses, the Ulam computational grid acted as a trap. When forced to map complex, twisted models, the data broke down into observable disintegration. By standardizing around the square tank geometry, Paper 61 transforms that grid from a computational hazard into an analytical shield. A flat geometric mixing penalty translates directly into uncompromising hardware boundaries that dictate exactly where and when a sensor must deploy. Finite matrix calculations are not meant to perfectly simulate every ripple of fluid dynamics. By calculating rigorous mixing penalties and demanding specific revisit schedules, the mathematics operate as a practical forensic tool. They provide the hard data required to keep the high-density herd alive.